channel. And today we will have a talk by Ryan, who will be talking about parameterized stacked intelligent metasurfaces for bistatic integrated sensing and communications. This work was presented at the latest Azilamar Conference on Signal Systems and Computing. Yeah, Ryan, please take it away.
Yeah, so hey everyone, I'm Ryan, and today I'm going to be talking about parametrized sims for ISAC. And of course, this is a collaboration between Construct University and the National and Kapodistrian University of Athens with George Alexandropoulos. So let's dive straight into it. So the idea is pretty simple. It's just we are extending the MIMO setup that we typically have in communication systems to incorporate these new and interesting material-based enhancements that have been coming out in the recent years. So what we are saying is that we have now a typical link, a communications link with the transmitter, a MIMO transmitter and receiver. And we are placing stacked intelligent metasurfaces in front of each of them. And they are placed very close to them such that any waves that are being transmitted or being received are first go through these stacked intelligent metasurfaces, so these SIMs, and then go into the antennas, are received at the antennas at the receiver or transmitted, and vice versa. So we also consider that we have an arbitrary number of reconfigurable intelligence surfaces, so the RISs, in the environment. So this can either be, you can have one RIS or up to K RISs. The number is arbitrary, but the idea is that you're going to have sub-channels between each of these links. So you're going to have one direct line of sight, so to say, channel between the SIMs, between the two SIMs, the transmit and receive SIMs, and you're going to have sub-channels between each of the RISs and the SIMs. So you're going to have one here and one here, and on the receive side, it's the same thing. So we now want to model these sub-channels such that we can describe these high mobility systems. So to do integrated sensing and communications, because usually you would have a bunch of scatterers placed in the environment, and each of these scatterers would have a delay and a Doppler shift, which if you estimate, you will have an idea about the target distances and velocities, right? So that's the idea of the work, and this is the primary motivation for this as well. And the SIM model, we adopt a classical state-of-the-art model for the SIM, where you have this product of diagonal phase shift matrices and coefficient matrices. So the diagonal phase shift matrices are given by this psi matrix, psi matrix, and your gamma q. These describe the coefficient matrices that are usually given by the Rayleigh-Sommerfeld diffraction theory. So this is general in the sense that you can use any state-of-the-art model that you want here, because these gamma q's purely depend on the theory and they are fundamental, so they cannot be changed. And if you prefer to use the Rayleigh-Sommerfeld diffraction theory, you can of course make your coefficients according to that. And this psi contains the optimizable variables for each of the surfaces. And there are diagonal matrices with phases that you can tune to change the electromagnetic response of these SIMs. So it's the same, pretty much the same on the receive side as well. This is the receive transfer function for the RX SIM. And now you have this delta, which are the matrices that contain the parameters to be tuned. So now proposed model that we have, which describes the system that I showed you before, is given by equation 3. So as you see here, you have your full channel, which is a response of the SIM, of the transmit SIM, the receive SIM, and all the receivers. And of course, we can slowly start looking at the components of this effective channel. So these gammas are what we described before, are the response vectors of the response matrices of the SIMs. These R's are correlation matrices at the outermost layers of the SIM, which usually happens due to the close spacing of the meta-atoms. And this H tilde is what comes from the direct line of sight channel and the recess. So as you can see, this orange part is the direct channel between the two recesses, and the sum over here on K is what you get when you incorporate the risk structures as well. So we can now define a uniform plane array response vector as in equation 5 and define our direct response to be equation 6 here, where you now have the channel coefficients. So these are the amplitudes which already take into account path loss and so on. You have your Doppler shift, and you have your delay for each of the p targets in that vicinity. So I might have to, I will also be explicit here just to be general. There can be, depending on the placement of the sims and recurs, each of the bouncers, so to say, from these scatterers could be different because there could be some scatterers that are just in the line of sight link, which are seen by line of sight link, and there could be some scatterers which are seen by the other links as well. So this P could be different for each of the sub-channel links, which is why we make the distinction between the P for the direct paths and P tilde and P bar for the transmit and receive paths. So now the proposed OFDM signal model can be expressed as in equation 9 here. For further details on the full derivation, you can refer to this published work in Transactions on Wireless Communications. And yeah, so this is the input-output relationship is in a nice form that we are all familiar with, in a nice linear form. So as you can see, this proposed model now can be written compactly as a matrix, as given in equation 10, where your RIS and SIM responses are modeled by this H check. And your waveform specific response, for example, if you're using OFDM, you can see here that this G is a channel response with the delays, Doppler shifts, and so on. And of course, the operations that you use to modulate the waveform. And the final expression can be split into two. So this orange part is, as I showed you before, the direct part between the two sims. And if you have any research in the surrounding, you would also have this purple term. So if you don't have any recurs, this term would vanish and you would only have the orange term. So what's interesting here is that, as you can see, the waveform only influences this G, and this H check is, it does not depend on the waveform. So for even if you use a different waveform, you would have the same H check matrix. And the only thing that would change when you have a waveform would be this GP matrix. So in a similar manner, you can also express the OTFS waveform. So as at the end of the day, it looks very similar. It's just that the matrices inside this GP OTFS is going to change because it's a different waveform. And you can do the same treatment for the AFDM waveform as well. So I will leave for the details because this is just still the preliminaries that we are covering, and we can now get to the point of what we can do in terms of ISAC. So as a summary, you have these upsides for the phase shift matrices, deltas also, and this phi k for the phase shift matrices, and of course these subchannel definitions as well. So for the rest of the work, we are going to focus on the direct link channel component only because we would have to optimize the risk phase shifts as well, which leads to different optimization, which would lead to a different optimization problem. So to simplify things, and since this is the first work on it, we will only talk about the direct link channel component where you have two recurs at both the transmitter and receiver and no two SIMs and no recurs in the environment. So this is just a figure to show that having these recurs in the surrounding at the transmitter and receiver will not affect the full final impulse response of the waveform specific channel. And yeah, as you can see, this look very familiar from previous literature on these three waveforms, and the channel response will remain unchanged, which makes sense because, as you saw from before, the only change when we add a RIS and or a SIM would be in that H check matrix, which will only influence the amplitudes. So this is the system model that we consider. So this is a bistatic ISAC system where you have a transmitter and a receiver, and you have a bunch of targets in the surrounding as well. Both the transmitter and receiver are equipped with SIMs, and you want to decode the data at the receiver, and you also want to get an idea of the target parameters. So you would like to have the range and velocities of all of these targets in the surrounding as well. So now we can simplify this model also a bit, and the SISO versions of what was presented before are given in equations 15 and 16. So as you're familiar now, we still have the same phase shift matrices that can be optimized, and we can now compactly write our channel response as equation 17, where this H tilde is given by this. So as you can see now, each of these taus and the nus will give us an idea of the delays and Doppler shifts of the targets in the surrounding. And of course, since this is a MIMO system, you would also have the angle of arrivals and angles of departure. But this is relegated to future work because this would involve the solutions using an oblique manifold to estimate these. So now we can express compactly the AFDM response as in equation 18 for the SISO case. The choice of waveform is arbitrary. You can use anything you want. And the only changes are here in 20A and 20B. And what's nice to see here is that the variable that we have to optimize can be compactly written in equation 19, where now this all contains all of the phase two. So for example, the correlation matrices, the response vectors, and also this U and V, which contain the tunable elements in the sims. So the optimization problem that we are going to solve here is given in equation 21. So what we are saying is that we want to maximize the path gain of each path, but we do this in a specific way such that we want to maximize the smallest path gain at each iteration. So this translates to doing a procedure which is very similar to a max-min optimization problem. So we are first going to choose the weakest path and then maximize that path. And after a couple of iterations, we can then choose the next weakest path at the current state and then maximize that path. So this procedure can be is done using a gradient ascent, of course. And I can so these are also some closed form expressions for the gradients that we can compute to do this optimization with the corresponding updates given here. But in order to give you a visual idea of how the optimization takes place, consider a plane, a mountainous plane, where you would have the objective function value specified by this O, Z, comma, Z tilde, and consider a single point here. So, and then when you have multiple paths, you would have multiple points in this mountainous region. And first you would choose the weakest point. So P1 seems to be the lowest in this region, seems to have the lowest magnitude in this region. So we now check the gradient direction, the direction in which this lowest path can be maximized in. And then we move all of the points in this direction. So of course, as you can probably see, this procedure, due to this non-convexity as well, is suboptimal because optimally we would like to have all the points in a direction which is optimal to all of them simultaneously. But this is a very good suboptimal solution, as you will see later on. So we can just repeat this procedure now. Now this P4 will be our weakest path, and we will now move all of the points in that direction. So they will go over there. So this is like a small visualization of what actually happens in the optimization problem. So now you can also see in terms of a convergence plot what really happens. So as you can see, P2 is the weakest path. So for the first 20 iterations, we're going to maximize P2. And now at 20 iterations, we're going to check, okay, which one's the weakest path? And now, as you can see here, P3 is the weakest. So we maximize that path as well. So as you can see, by doing this procedure, all of the paths are maximized. And this is a very nice thing in terms of sensing, because what we're saying is we are maximizing all of the path gains from all the paths, and none of the paths actually vanish, since we want our objective intrinsically embeds all the paths. So this is a typical convergence plot. And now we can, for the estimation procedure itself, we can write our input-output relationship as an equation 27, which we have reformulated as a sparse recovery problem in order to build the estimator. And we can use a PDA-based bistatic algorithm. So PDA stands for probabilistic data association. So this is a higher complexity version of the expectation propagation and vector approximate message passing algorithms, which embeds a prior in the sense of estimation theory, but because we will have to assume that our estimates, our channel paths follow a Bernoulli Gaussian distribution, for example, since this is a sparse recovery problem. So then we can do a soft interference cancellation, and we can proceed to derive the variances, the conditional covariance matrix. And we can also do the belief generation stage where we extract the extrinsic PDFs. And finally, we can do a soft replica generation to obtain our outputs. So some of the results are given here. So as you can see, by doing this procedure, the red line is the proposed. We get a lot of gain in terms of sensing. So these white balls represent the state of the art, so without any sims in the environment, and the red is a proposed contribution. And this black line is also an interesting result because this black line is obtained by solving a similar optimization problem, but instead of maximizing the weakest path, we are just going to maximize the sum as a whole. So as you can see, this is actually bad for sensing because by maximizing the sum as a whole, we are actually making some parts very strong, but at the same time making some other parts really weak. So in this sense, it's really bad for sensing. And it's a similar case for the velocities as well. And finally, we can also show the communications performance using a beta rate curve, where the same notation follows, where these white markers are for the typical case with no artificial structures. This black one is the previous method that I described where you would optimize the sum as a whole. But yeah, since that seems to be more communication optimal since you are really maximizing the full path gain. But as you saw before, for the sensing, it was not so good. And a proposed method, the max-min optimization, is this red line, where, as you can see, the performance also improves, maybe not as much as the case where you just don't care about the sensing, but this is an interesting trade-off. So, as some take-home messages, we have that SIMs can actually be very effective in changing the performance gap or bridging the gap among different waveforms, for example, OTFS, OFDM, and AFDM. And this is also a timely contribution, so to say, because uh, there's been some recent talks with 3GPP about finalizing a waveform for 6G. So in this sense, we could either choose, it seems to be the case that we can either choose to have different waveforms or have artificial structures enhancing our transceivers. So this is a very interesting take-home message, I would say. And the take-home message too is that while of course we want to target the Pareto optimality in ISAC system design in an optimal setting, we see that optimizing these structures for sensing is giving us near Pareto optimal performance because we saw an interesting trade-off. So this seems to be hinting to us that making our objective a sensing objective and having communications constraints is probably better than vice versa. And finally, as a result of the proposed model, we can now design receivers or transmitters for both for ISAC waveforms under unified framework. So you don't need to be doing different architectures for these transceivers if you want to do different waveforms. So you can use a common framework for all of the different waveforms. So this is it for the presentation. Thank you for your attention. Do you have any questions?
Thank you, Ryan. Guys, any questions? If not, maybe while you think about a question, I have a question actually, Ryan. Um, is it possible, in your knowledge, to design method passing receivers that try to optimize two or more competing objectives at the same time, and which therefore are trying to go for an Pareto optimality? Because you mentioned that Pareto optimality would be sort of the holy grail, right? That's what one
Mm-hmm.
would like to have. And of course, these results suggest that you might be able to cheat a little bit by not really going for it, because if you optimize for sensing, you kind of get you don't hurt computing communication that much. But that doesn't mean that one cannot improve the communication further, right? So
Mm-hmm.
that's my question. Have you ever seen anything, or what can you say regarding designing a message passing a receiver that tries to look at both objectives at the same time?
Well, okay, thank you for the question. Actually, interesting question because usually in the sense of a message passing algorithm, you would want an unconstrained optimization problem, right?
Mm-hmm.
And usually that is the case because fundamentally what you're trying to do is you want to minimize the lasso formulation of the problem. And in terms of a raw lasso, it's a bit tough to have competing objectives. So in from a estimation theoretical point of view, I'm not sure if we can embed competing constraints inside the lasso unless we have also two different regularizers for the two different objectives, and we try to design something that way. But I'm not sure. Maybe one would have to look into the mechanics of the problem, first formulate it carefully, and then look into the mechanics of it to see if you can really design a proper message passing based receiver for it. I mean, I think that's that's pretty much all I can say at the moment.
Mm-hmm. Yeah, I am asking this because I have seen long time ago a paper by colleagues from Japan on something similar that was talking about information sharing strategies to achieve Pareto optimality. I have to dig the paper, but that was a relatively old paper from 2000, I don't know, 9 or 10 or something like that, about more than 10 years ago. And therefore, I guess before the whole hype of message passing,
Mm.
I think this was all before the latest version, at least of a GABP and so on, came around. So it might be useful to revisit those ideas and see if one can actually think about something like that. But yeah,
Okay.
thanks for the answer.
Okay.
Anybody else?
Brilliant.
Any other comments, questions, guys? You're all very quiet. No? Okay, Ryan, I guess that's it for now. So I
Yeah.
thank you
Okay.
all for attending anyway, and I see you next time in the wireless channel.
Thanks. Bye bye.
Bye.